Hello, and welcome to Space for Sleep. The moon looks familiar because it is close enough to seem ordinary. That familiarity is misleading. It is not just the pale disk above the roofs, not just a calendar in the sky, not just the place where astronauts left footprints more than half a century ago. The moon is the surviving evidence of a planetary catastrophe. It is a fragment of Earth's own violent beginning, a body born from impact, fire, vaporized rock, and orbital debris. It is the object that steadied Earth's axis, slowed Earth's rotation, pulled at the oceans, recorded billions of years of impacts, and preserved in its dust a history that Earth itself has mostly erased. The moon is the most familiar object in the night sky, and probably the least truly understood. People have been watching it for as long as people have existed. Every human civilization in recorded history has named it, tracked it, built calendars around it, assigned it meaning, made it the subject of poetry, mythology, mathematics, navigation, religion, and science. It has been blamed for madness, credited with controlling fertility, used to guide ships, used to plan harvests, and treated as the home of gods or the dead. Children learn to identify it before they learn to read. It is the first celestial object most people point to when asked to look at the sky, and yet most people know almost nothing about it in any scientific sense. They know it is round. They know it waxes and wanes through a monthly cycle. They know human beings walked on it. Beyond that, the details blur into something vague and sentimental. Those details are extraordinary. The moon did not always orbit Earth at its current distance. It was once much closer, and it is still slowly moving away. It may have formed from a catastrophic collision between the young Earth and a planet-sized object 4.5 billion years ago, an impact so violent that it partially vaporized both bodies and scattered debris into orbit. Without the moon, Earth's axial tilt may have wandered far more chaotically over geological time, producing climate instability severe enough to alter the history of life. The moon is covered in glass beads made by ancient impacts and volcanic fire. Its far side looks completely different from the near side and was unknown to any human being until 1959. It holds water ice in permanently shadowed craters at its poles. It has a small iron core, a layered interior, a crust that is thicker on the far side than the near side, and a long record of moonquakes detected by instruments left by Apollo astronauts. The moon is not a simple rock. It is a world with a complex history, a scientifically rich present, and a future that is still unfolding on timescales that dwarf all of human civilization. The moon formed approximately 4.5 billion years ago, within the first 100 million years of the solar system's existence. And the way it formed is one of the most dramatic origin stories of any object in the solar system. The leading hypothesis, supported by the bulk of the physical evidence, though not without remaining uncertainties, is called the giant impact hypothesis, sometimes referred to as the Big Whack. It proposes that the young Earth, still in the process of accreting material and differentiating its iron core from its rocky mantle, was struck by a large planetary body roughly the size of Mars. This impactor is usually called Theia, after the Titan in Greek mythology, who was the mother of the moon goddess Selene, a name that reflects both the mythological resonance and the specificity of the hypothesis. Theia, in the current best models, was a protoplanet that had formed in the same region of the solar system as Earth, possibly in one of the gravitationally stable Lagrange points of Earth's orbit, and which had accreted to perhaps a tenth of Earth's current mass before its orbit became unstable and it began moving on a trajectory that would eventually intersect Earth's. The collision, when it came, was not a simple crash in the ordinary sense. At the speeds involved, tens of kilometers per second, and with the masses involved, two planetary bodies, the physics of the encounter was catastrophic in a way that is difficult to visualize. Theia did not simply strike Earth and bounce or shatter. The collision was energetic enough that both objects were partially or largely vaporized on impact, the solid rock of both bodies being converted to plasma and silicate vapor at the point of contact, with enormous amounts of material being thrown outward into orbit around the surviving body. The collision lasted only a few hours in terms of the direct physical contact, but the consequences unfolded over thousands to millions of years. The material ejected into orbit, a cloud of vaporized and molten rock encircling the newly merged proto-Earth, gradually cooled and condensed. Lighter silicate materials, which had been disproportionately ejected into orbit relative to the denser iron that sank into the merged body's core, accumulated in orbit and began gravitationally accreting, clumping together under their own mutual gravity. Within perhaps a few thousand to a few hundred million years, the exact timescale is still debated, the orbiting material had coalesced into a single large body, the Moon. The giant impact hypothesis was first proposed in a formal scientific context in 1975 and gained wide acceptance following the 1984 Kona Conference on the Origin of the Moon, at which it was presented comprehensively for the first time and found to explain several key observations better than alternatives. The primary observational support comes from three independent lines of evidence. First, the Moon's composition. The Moon is made primarily of silicate rock with very little iron. Its overall density, about 3.3 grams per cubic centimeter, is much lower than Earth's overall density of 5.5 grams per cubic centimeter. This low density reflects the fact that the Moon formed predominantly from silicate material that was ejected from the outer layers of both Theia and proto-Earth, while the denser iron from both objects' cores was retained by the merged proto-Earth. A collision between two differentiated bodies that had already separated into iron cores and silicate mantles, would naturally produce iron-poor orbiting material. This is exactly what the Moon's composition reflects. Second, the oxygen isotope composition. Oxygen has three stable isotopes: oxygen-16, oxygen-17, and oxygen-18, and the ratio in which they occur varies systematically across the solar system, with bodies that formed at different distances from the Sun having characteristically different ratios. Earth and the Moon have almost identical oxygen isotope ratios, far more similar to each other than to any other body in the solar system, including Mars, the asteroids, and other meteorite parent bodies. This extraordinary isotopic similarity between Earth and the Moon suggests that they formed from the same material, or material that was thoroughly mixed, which is consistent with a giant impact that partially vaporized and homogenized the material from both Theia and proto-Earth before the Moon accreted from the mixed debris. Third, the angular momentum of the Earth-Moon system. The total angular momentum, the combined rotational motion of Earth spinning on its axis plus the Moon orbiting Earth, is much higher than would be expected for Earth alone, or for Earth and a Moon that formed independently. A giant impact that transferred momentum from the impactor's orbital motion into the Earth-Moon system naturally explains the observed angular momentum, which otherwise requires a coincidence that has no natural explanation. These three lines of evidence, combined with computer simulations that can reproduce the gross features of the Moon's formation under the right impact conditions, make the giant impact hypothesis the overwhelming scientific consensus. But the details of the impact remain subjects of ongoing refinement. Early models proposed a Theia roughly the mass of Mars striking Earth at a grazing angle, with most of the Moon's material coming from Theia's mantle. Later models, driven by the oxygen isotope similarity problem, if most of the Moon came from Theia, why is the Moon's oxygen isotopic composition almost identical to Earth's rather than resembling Theia? Have revised toward impacts where a larger Theia strikes more head-on, mixing Earth and Theia material more thoroughly. One intriguing alternative model, developed in 2012 by scientists at Harvard and UC Davis, proposed that the impact was so energetic, produced by a large, fast-rotating proto-Earth being struck by a Theia of comparable size, that both objects were nearly entirely vaporized, forming what the researchers called a synestia, a rapidly rotating, donut-shaped cloud of vaporized rock that surrounded the post-impact body and extended beyond the orbit at which the Moon would eventually form. In this scenario, the Moon forms not from a disk of discrete rocky debris, but from within the vapor cloud itself, condensing as the cloud cools. The advantage of this model is that it produces thorough isotopic homogenization between the material that eventually forms the Earth and the material that forms the Moon, explaining the near-identical oxygen isotope ratios, without requiring the impactor to have had the same oxygen isotope ratio as Earth in the first place. Each of these variants of the impact hypothesis makes slightly different specific predictions about the Moon's composition and interior structure. The most recent generation of lunar sample analysis and the data from lunar missions are beginning to constrain these models in new ways. For example, the isotopic composition of zinc, a moderately volatile element, in lunar samples has been measured with extraordinary precision and compared to the Earth. The Moon is slightly depleted in zinc relative to Earth, and this depletion appears to be isotopically fractionated in a way consistent with volatile loss during a high-temperature, high-energy impact event. These kinds of geochemical fingerprints, preserved in the lunar samples, are among the most powerful tools available for testing the details of the giant impact scenario. Before the giant impact hypothesis gained dominance, several alternative theories of lunar origin were seriously considered. The fission hypothesis proposed that the early, rapidly rotating Earth simply spun fast enough that a blob of material was flung off from the equatorial region and went into orbit, eventually forming the Moon. This idea, first proposed by George Darwin, Charles Darwin's son, in the 19th century, was elegant but ran into the problem that a rapidly spinning Earth couldn't produce enough angular momentum to eject material into a stable lunar orbit without spinning so fast that Earth itself would be disrupted. The capture hypothesis proposed that the Moon formed elsewhere in the solar system and was captured by Earth's gravity as it passed by. This is possible in principle, but requires an unlikely combination of circumstances. The incoming object needs to lose energy during the encounter, which usually requires a third body or atmospheric drag, neither of which was plausible in the early solar system. The co-formation hypothesis proposed that Earth and Moon formed simultaneously from the same swirling cloud of material as a binary planet system. This would naturally explain their similar compositions, but would predict a much higher iron content in the Moon than is observed. The giant impact hypothesis resolved most of these difficulties simultaneously, explaining the low iron content, the oxygen isotope similarity, and the angular momentum in one coherent scenario, which is why it gained such broad acceptance. The precise nature of the impact, the size of Theia, the angle of impact, the relative velocities, is still being refined through a combination of computer simulation and laboratory analysis of lunar samples. The giant impact hypothesis, far from being a settled question, remains an active area of research at the frontier of planetary science. There is another way to think about that impact, and it makes the Moon feel less like a separate object and more like part of Earth's deepest biography. Before the Moon existed, Earth was not the stable blue world we know. It was a hot, growing planet, still being struck by large bodies, still separating metal from rock, still building an atmosphere and a surface. The impact with Theia did not happen to a finished Earth. It happened to a young planet still in the process of becoming itself. The collision likely removed or reworked much of the early atmosphere, melted enormous fractions of the mantle, and reset parts of Earth's chemical and thermal history. In other words, The moon's formation was not only the birth of the moon, it was one of the final major events in the making of Earth. If the moon formed from debris thrown into orbit, then every lunar highland, every cratered plateau, every basaltic plain is made from material that was once part of that violence. The moon is a cooled remnant of a fire so large that it is difficult to imagine. When we look at it now, quiet and gray, the contrast is almost absurd. The object appears calm because 4.5 billion years have passed. Its calmness is not the absence of drama. It is the aftermath of drama on a planetary scale. The early Earth-Moon system would have looked nothing like the present one. The moon would have orbited much closer, perhaps only a fraction of its current distance. It would have loomed enormous in Earth's sky, not as a small disk that can be covered with a thumb, but as a vast bright world filling many times the angular size it has today. The tides raised on the young Earth would have been enormous. Oceans, once they condensed, would have surged under the pull of a nearby moon with a violence no modern coast has ever seen. Earth's day would have been much shorter, perhaps only a few hours long, because the young Earth was spinning rapidly after the impact. Over time, tides changed everything. The moon raised bulges in Earth's oceans and solid body. Earth's faster rotation carried those bulges slightly ahead of the moon. The gravity of the bulges pulled forward on the moon, giving it orbital energy, and the moon slowly moved outward. At the same time, the moon pulled back on Earth, slowing Earth's rotation. This exchange of angular momentum is still happening now, slowly and measurably. It is not a metaphor. The moon is leaving Earth by a few centimeters each year, and Earth's days are gradually lengthening because of it. This makes the moon one of the rare astronomical objects whose long-term evolution we can measure directly with human instruments. Apollo astronauts left retroreflectors on the lunar surface, arrays of mirrors designed to reflect laser pulses sent from Earth. By measuring the time it takes light to travel to the moon, bounce off the reflectors, and return, scientists can measure the Earth-Moon distance to extraordinary precision. The result is one of the most elegant measurements in planetary science. The moon is receding from Earth at roughly the speed that human fingernails grow. That detail is quiet, but it is profound. The moon is not fixed. The system is still evolving. The same tides that shaped Earth's oceans and slowed Earth's rotation are still moving the moon outward, centimeter by centimeter, year by year, century by century. The night sky is changing, too slowly for a single lifetime to notice, but not too slowly for physics to detect. This also means that the moon we know is only one temporary version of the moon. In the deep past, it was larger in the sky and more powerful in its tidal pull. In the far future, it will appear smaller, produce weaker tides, and sit farther from Earth. The moon has a history not only in its rocks, but in its orbit. Its distance is a record. Its recession is a clock. What happened to the moon in the first several hundred million years after formation is, in some ways, as dramatic as the formation itself. The newly formed moon was hot, extraordinarily hot. The energy of the giant impact, the energy of accretion from the orbiting debris, and the energy of radioactive decay in the freshly assembled material together produced a moon in its early state that was probably largely or entirely molten. The surface of the newly formed moon was not solid rock, but a global magma ocean, a planet-wide body of molten rock, possibly hundreds of kilometers deep. A magma ocean is not a stable situation. As the moon began radiating heat to space, the outer surface cooled and began to crystallize. Different minerals crystallize at different temperatures, and minerals of different densities sink or float, depending on whether they are denser or less dense than the surrounding magma. Heavy minerals, pyroxenes and olivines, crystallized early and sank toward the interior. Lighter minerals, particularly the calcium-aluminium silicate mineral anorthosite, crystallized later at lower temperatures, and, being less dense than the remaining magma, floated upward to form a solid crust across the surface of the still molten interior. This process is called fractional crystallization, and its result, the lunar highlands, is still visible today on the Moon's heavily cratered ancient terrain. The highlands are predominantly made of anorthosite, that ancient, light-colored mineral that crystallized and floated to the top of the magma ocean as it cooled. When you look at the bright, heavily cratered regions of the Moon, you are looking at rock that solidified from a global ocean of magma approximately 4 billion years ago. The relative brightness of the highlands compared to the darker maria is largely due to the difference in composition. Anorthosite is pale gray, while the basaltic rock that fills the maria is darker. As the magma ocean cooled and solidified, the Moon differentiated, its interior organized into distinct layers with different compositions and densities. The heavy minerals that had sunk during fractional crystallization concentrated in the mantle. The lighter anorthositic crust formed on top, and at the very center, a small iron core may have formed. Though the Moon's core is much smaller relative to its total size than Earth's, consistent with the prediction that the Moon formed primarily from silicate material with relatively little iron. While all of this was occurring, the early solar system was not a quiet place. The period from approximately 4 billion to 3.8 billion years ago is called the Late Heavy Bombardment, a period during which the Moon, Earth, Mars, Mercury, and other rocky bodies were struck by an elevated rate of large impactors. The evidence for this bombardment is written in the Moon's surface, which preserves craters from this period that Earth's geological processes have long since erased. The large impact basins that dominate the Moon's southern highland terrain, Nectaris, Imbrium, Oriental, and the enormous South Pole Aitken Basin, date from this early period of intense bombardment. The late heavy bombardment may have been triggered by changes in the orbits of the giant planets, particularly Jupiter, that destabilized the outer solar system and sent a wave of asteroids and comets inward, striking the rocky planets. The timing of the bombardment, its sudden onset and relatively rapid decline, is consistent with this nice model scenario in which planetary orbital instability caused by resonances between the giant planets drove a brief, intense period of large impacts before the solar system settled into its current relatively stable configuration. After the late heavy bombardment ended, the Moon's surface continued to be shaped primarily by impacts, but at a diminishing rate. The largest basins, already formed, were partially flooded by basaltic lava erupting from the interior in the period roughly 3.9 to 3 billion years ago, filling the deep low-lying regions and creating the dark plains we call the Maria, the Latin word for seas, named by early astronomers who mistook them for actual bodies of water. These ancient volcanic eruptions produced the dark basaltic rock that now fills Mare Tranquillitatis, Mare Serenitatis, Mare Imbrium, Oceanus Procellarum, and the other Mare regions visible on the near side of the Moon. Before examining the surface in detail, it is worth establishing the basic physical character of the Moon and its relationship with Earth. The Moon has a diameter of about 3,474 kilometers, roughly a quarter of Earth's diameter, making it the fifth largest moon in the solar system and by far the largest in proportion to its parent planet. No other major planet in the solar system has a moon as large relative to itself as Earth has the Moon. This disproportion, the Moon being so large relative to Earth compared to the typical satellite to planet size ratio, is one of the indirect pieces of evidence supporting the giant impact hypothesis, since only a collision on the scale of Theia could plausibly have produced such a large orbiting body. The Moon's mass is about 1.2% of Earth's mass, and its surface gravity is about 16.5% of Earth's, about 1/6. An astronaut on the moon weighs about 1/6 of their Earth weight, which produces the characteristic bounding, floating quality of movement seen in the Apollo mission footage. The low gravity also means that the moon cannot retain a substantial atmosphere. Any gas molecules at the surface move fast enough at the prevailing temperatures that they can reach escape velocity and be lost to space within a relatively short time, preventing any permanent dense atmosphere from accumulating. The moon's escape velocity is about 2.4 kilometers per second, much lower than Earth's 11.2 kilometers per second. This is why rockets from the moon during the Apollo missions required far less fuel to reach lunar orbit than rockets from Earth require to reach Earth orbit, despite the fact that the Apollo spacecraft were already in Earth orbit when they began the journey. The moon's weak gravity is a significant engineering advantage for any future surface operations. It reduces the energy required to lift materials off the surface by a dramatic factor compared to Earth. The moon orbits Earth at an average distance of about 384,000 kilometers. This distance is not constant. The moon's orbit is slightly elliptical, so it varies between approximately 356,000 kilometers at perigee, closest approach, and approximately 406,000 kilometers at apogee, farthest point. The variation in distance produces a corresponding variation in the moon's apparent size in the sky. The supermoon phenomenon occurs when a full moon coincides with perigee, making it appear slightly larger and brighter than usual, though the difference is subtle enough that most people don't notice it without being specifically told. The moon is tidally locked to Earth. It rotates on its axis in exactly the same period that it takes to orbit Earth, approximately 27.3 days. This synchronous rotation means that the moon always presents the same face toward Earth. We never see the far side from Earth's surface. This tidal locking is not a coincidence. It is the stable endpoint of tidal friction acting over billions of years. Earth's gravity exerted a tidal force on the slightly non-spherical early moon, creating a slight bulge on the side facing Earth. As the moon rotated faster than its orbital period in the early solar system, the drag of this tidal bulge gradually slowed the rotation until it matched the orbital period, at which point the tidal torque vanished and the rotation stabilized. Every large moon in the solar system that is close enough to its parent planet has undergone the same tidal locking process. The same tidal forces that locked the moon's rotation are also gradually transferring angular momentum from Earth's spin to the moon's orbit. Earth's rotation is very slowly being braked by the moon's gravitational tug, and in exchange, the moon is very slowly spiraling outward. Currently, the moon is moving away from Earth at a rate of about 3.8 centimeters per year, a figure measured precisely using laser ranging, by bouncing laser pulses off retroreflectors left on the lunar surface by Apollo astronauts, and measuring the round-trip travel time with exquisite precision. This drift has been ongoing since the moon's formation. Billions of years ago, the moon was much closer to Earth, perhaps only about 25,000 kilometers away in its earliest days, compared to today's 384,000. The moon was once enormous in Earth's sky. If you could have looked up from the early Earth, the moon would have filled perhaps 15 or 20 degrees of sky, many times larger than it appears today. This gradual retreat of the moon has consequences that extend beyond the dramatic change in appearance. As the moon moves farther away, its gravitational influence on Earth's tides weakens. Earth's tidal bulges, which are dragged along by Earth's rotation ahead of the moon's orbital position and which exert the torque that both slows Earth's spin and accelerates the moon's orbit, will gradually diminish. And as Earth's rotation slows, days get longer. In the deep past, when the moon was much closer, Earth rotated much faster. Early in Earth's history, a day may have been only 6 to 8 hours long. The gradual slowing of Earth's rotation over billions of years has lengthened the day to its current 24 hours, and will continue to lengthen it in the future until, in the very distant future, Earth's rotation period matches the Moon's orbital period and the system reaches a double tidal lock, with Earth always showing the same face to the Moon, just as the Moon always shows the same face to Earth. This endpoint is billions of years in the future, and the Sun will have entered its red giant phase long before it is reached. The familiar phases of the Moon are also worth slowing down for, because they are one of the first astronomical patterns most people learn and one of the easiest to misunderstand. The Moon does not change shape. It is always a sphere, always half illuminated by the Sun, just as Earth is always half illuminated. What changes is the angle from which we see that illuminated half. At new moon, the Moon is between Earth and the Sun, and the side facing Earth is mostly dark. At first quarter, we see half of the sunlit hemisphere. At full moon, Earth is between the Sun and the Moon, and the lunar near side is fully illuminated. At last quarter, the geometry has turned again. The cycle takes about 29.5 days from new moon to new moon, because Earth is moving around the Sun while the Moon orbits Earth, so the Moon must travel a little more than one full orbit to return to the same Sun-Earth-Moon geometry. This simple geometry has shaped human timekeeping for tens of thousands of years. A lunar month is written directly into the sky. Before mechanical clocks, before printed calendars, before astronomy became a mathematical science, the Moon offered a repeating pattern that anyone could see. Its phases divided darkness into a cycle. Its full light changed the behavior of animals, the movements of people, the safety of travel at night, and the timing of rituals and agriculture. Eclipses are the same geometry becoming exact. A solar eclipse occurs when the Moon passes directly between Earth and the Sun and casts its shadow onto Earth. A lunar eclipse occurs when Earth passes directly between the Sun and the Moon and casts its shadow onto the lunar surface. These events do not happen every month because the Moon's orbit is tilted about 5 degrees relative to Earth's orbit around the Sun. Most months, the Moon passes slightly above or below the perfect line. Only when the new or full moon occurs near one of the orbital nodes, the 2 points where the Moon's orbit crosses Earth's orbital plane, can an eclipse occur. Solar eclipses are possible because of a remarkable coincidence. The Sun is about 400 times wider than the Moon, but it is also about 400 times farther away. From Earth's surface, the two disks appear almost the same size in the sky. This is why the Moon can cover the Sun so precisely during a total solar eclipse, revealing the solar corona as a pale, structured halo around a black disk. No physical law required this coincidence. It is a temporary accident of cosmic scale and orbital timing. In the deep past, when the Moon was closer, total eclipses were different. The Moon appeared larger and covered the Sun more completely. In the far future, as the Moon continues to recede, total solar eclipses will end. The Moon will appear too small to cover the Sun fully, and only annular eclipses will remain. That fact gives every total solar eclipse a kind of deep time fragility. It is not only beautiful, it is temporary. We live in the interval of Earth's history when the Moon is at the right distance to make the Sun disappear almost perfectly. The Moon also produces libration, a slow apparent wobble that lets observers on Earth see slightly more than half of its surface over time. Because the Moon's orbit is elliptical and its rotation is steady, we sometimes see a little around the eastern edge and sometimes a little around the western edge. Because the Moon's axis is slightly tilted relative to its orbit, we also see slightly over its north and south poles at different times. Over a long period, this allows Earth-based observers to see about 59% of the lunar surface, not just exactly 50. But the remaining 41%, the true far side, was completely unknown until spacecraft photographed it. This matters because it reminds us that even the most familiar object in the sky kept secrets until the space age. Humanity had watched the moon for all of recorded history, mapped it through telescopes, named its seas and craters, built calendars around its phases, and still had never seen almost half of it. Familiarity was not the same as knowledge. The moon's influence on Earth goes far beyond the obvious daily tides that push ocean water up shorelines and then pull it back twice a day. The gravitational relationship between Earth and Moon has shaped Earth's geology, its climate, the evolution of life, and the fundamental physical constants of the Earth environment that life experiences. The tides driven by the Moon, and to a lesser extent by the Sun, are responsible for generating significant amounts of energy through the friction of water moving against the seafloor and coastlines. Tidal power is genuinely significant on a geological scale. Over the history of the solar system, tidal friction has transferred an enormous amount of energy from Earth's rotation into the ocean, gradually heating the water and dissipating into the environment. This energy transfer is the mechanism by which Earth's rotation is being slowed. In the early solar system, when Earth rotated in 6 hours rather than 24, the tidal forces were dramatically more powerful. The moon was closer, the rotation faster, the tidal bulges larger and more energetic. The early ocean must have experienced tides of extraordinary scale, perhaps hundreds of meters high in some coastal regions, driven by a massive, close moon pulling at a rapidly rotating planet. The role of the moon in stabilizing Earth's axial tilt is perhaps its most consequential contribution to life's existence on Earth. Earth's axis is currently tilted about 23.5 degrees from the vertical perpendicular to its orbital plane. This tilt is responsible for the seasons, the alternation between summer and winter as different hemispheres are angled toward or away from the sun over the course of the year. The current tilt is moderate enough that the seasons are manageable. The temperature variation between summer and winter at mid-latitudes is significant but not extreme, and both poles experience roughly similar overall conditions averaged over geological time. But axes of rotation can wander. Under the influence of gravitational perturbations from the other planets, particularly Jupiter and Saturn, whose masses are sufficient to exert significant torques on Earth's axis over long timescales, Earth's axis could, in principle, precess not just with its current 26,000-year wobble, but with much larger amplitude changes on longer timescales. Calculations made in the 1990s showed that without the moon, Earth's axial tilt would vary chaotically between about 0 and 85 degrees over millions of years, driven by resonances between the precession of the axis and the orbital perturbations from other planets. Such extreme axial variations would produce climate swings far beyond anything in the geological record. At zero tilt, there would be no seasons and the poles would remain in permanent darkness. At 85 degrees, Earth would be tilted almost on its side like Uranus, with extreme polar summers and winters. The moon prevents this chaotic wandering by contributing a dominant gravitational torque to the precession of Earth's axis. The moon's gravitational pull on Earth's equatorial bulge drives a steady, regular precession at a frequency that, crucially, doesn't resonate with the orbital perturbations from Jupiter and Saturn. By setting the dominant timescale of the axis's precession, the moon keeps Earth's tilt in a stable range, currently varying only between about 22.2 and 24.5 degrees over a 41,000-year cycle. This is a small, well-behaved variation, not the wild oscillation that would occur without the moon. The implications for life are difficult to overstate. The relative stability of Earth's axial tilt over hundreds of millions of years has contributed to the relative stability of Earth's climate over that period, creating the conditions under which complex multicellular life could evolve over geological timescales without facing axial tilt-induced climate catastrophes. Mars, which lacks a large moon, has an axial tilt that has varied chaotically between about 15 and 35 degrees over its history and possibly more extremely in its deep past. The comparison is suggestive. Earth's large moon may be one of the reasons Earth's climate has been stable enough to allow the evolution of complex life, while Mars's lack of a stabilizing moon is one of the factors that has made its climate history more volatile. The connection between the moon and life on Earth is not simple, and it should not be exaggerated into mythology. The moon did not create life by itself. It did not guarantee evolution, and Earth would not necessarily have been completely sterile without it. But the moon changed the physical environment in which life evolved, and it did so in ways that may have mattered deeply. Tides create zones of alternation, places that are underwater, then exposed, then underwater again. Intertidal environments are chemically and physically dynamic. They concentrate organic molecules, cycle wet and dry conditions, expose minerals to sunlight and water, and create gradients of salinity, temperature, and chemistry. Some origin of life hypotheses consider such cycling potentially important because repeated wetting and drying can help simple molecules assemble into more complex structures. Whether Earth's first life actually began in tidal pools, hydrothermal vents, volcanic ponds, or some other environment remains unresolved. But the moon made Earth's tides stronger, especially early in history when it was much closer. Even after life began, tides shaped coastal ecosystems and biological rhythms. Many organisms time reproduction, feeding, migration, and movement according to lunar and tidal cycles. Corals, horseshoe crabs, marine worms, fish, shellfish, and many coastal species use the moon's cycle directly or indirectly. The monthly rhythm of light and tide has become part of the biological environment. The moon is not only an astronomical body overhead, it is part of the timing structure of life near Earth's oceans. The moon also influenced Earth's rotational history. A shorter early day would have changed atmospheric circulation, ocean tides, and perhaps climate patterns. As the moon slowed Earth's spin, the planet's day lengthened gradually. This change altered the rhythm of sunlight and darkness experienced by life. The 24-hour day we take as basic is not a fixed property of Earth. It is a current stage in a long tidal evolution. Ancient organisms lived under shorter days. Future organisms, if they exist far enough into the future, will live under longer ones. There is also the stabilization of Earth's tilt. The exact importance of this is debated, and modern models do not all agree on how chaotic Earth's axis would have been without the moon. But the broad point remains. The moon contributes a major stabilizing torque to Earth's spin axis. It helps keep Earth's obliquity within a relatively moderate range. That stability is one of the quiet background conditions under which long-term climate patterns have remained habitable enough for complex ecosystems. This is one of the more humbling ideas in planetary science. Habitability is not only about distance from a star. It is not only about water or atmosphere or a magnetic field. It can also depend on architecture, the presence of a large moon, the pace of rotation, the stability of axial tilt, the timing of tides, the distribution of continents and oceans, the chemistry of rocks, and the history of impacts. Earth is habitable not because of one lucky property, but because many physical systems ended up interacting in a range that life could tolerate and exploit. The moon is part of that architecture. It is not merely decoration in the sky. It is one of the reasons Earth's environment became the particular environment in which Earth's life evolved. The moon is also a clock, but not in the simple sense of marking months. Its surface is a clock of impacts. Its orbit is a clock of tidal evolution. Its phases are a clock of geometry. Its rocks are clocks of radioactive decay. Its distance is a clock of angular momentum moving slowly from Earth's spin into lunar orbit. Different kinds of time are layered through the same object. The monthly cycle is human-scale time. It is visible, rhythmic, immediate. A child can watch it. Ancient cultures could predict it. It is the moon as calendar. The crater record is geological time. A fresh crater ray may be young by lunar standards and still older than many human civilizations. A heavily cratered highland may preserve a surface more than 4 billion years old. That is the moon as archive. The recession from Earth is dynamical time. It is not visible to the eye, but it can be measured with lasers. It connects the present Earth-Moon system to the close, violent system of the deep past and to the more distant system of the far future. That is the moon as evolving machine. The radioactive clocks in lunar minerals are absolute time. They allow scientists to assign ages to rocks, basins, eruptions, and crust-forming events. That is the moon as laboratory. This layering of time is one reason the moon is so scientifically powerful. It lets us move between scales, a month, a mission, a billion years, the age of the solar system. Few objects are so close and so deep at once. The moon is near enough to touch, but old enough to contain almost the entire history of the Earth-Moon system. The surface of the moon is, in many ways, a museum of solar system history. Earth's geological processes, plate tectonics, erosion by water and wind, volcanism, biological activity, continuously recycle and transform the surface, erasing older features and replacing them with new ones. The oldest rock formations visible at Earth's surface are only a few billion years old at most. Even the oldest exposed ancient cratons have been transformed by subsequent geological activity. The moon has no plate tectonics, no liquid water, no atmosphere capable of significant erosion, and no biological activity. Its surface preserves geological features with extraordinary fidelity. Craters formed 4 billion years ago are still clearly visible. Lava flows that solidified 3 billion years ago still show their original surface texture. The footprints left by Apollo astronauts more than 50 years ago will remain essentially unchanged for millions of years. The surface is divided into two broad geological categories. The lunar highlands, also called the terrae, are the ancient, pale, heavily cratered terrain that covers most of the moon's surface, particularly the southern near side and virtually the entire far side. These are the oldest regions, composed primarily of anorthositic rock crystallized from the magma ocean more than 4 billion years ago and subsequently battered by billions of years of impactors. The highlands are pale because anorthosite is inherently light-colored, and they appear rough and complex because the density of craters is high. Every crater larger than about 10 kilometers that forms here simply overlaps with older craters rather than finding fresh, unbroken ground. The lunar maria, the dark, relatively smooth plains that cover much of the near side in a rough pattern sometimes fancifully compared to a face, are geologically younger. They formed when lava erupted from the moon's interior flooded low-lying regions, most of them ancient impact basins, in the period from roughly 3.9 to 3 billion years ago. The lava was basaltic, dark, iron-rich, low-viscosity rock similar to the basalt that forms Hawaii and Iceland on Earth. It flowed across the basin floors in thin, broad sheets, eventually cooling and solidifying into the smooth, dark plains we see today. The dark color of the maria relative to the highlands reflects the different mineral composition of basalt compared to anorthosite. Basalt contains more iron and titanium, which absorb visible light, making the surface darker. The maria are concentrated on the near side of the moon. There are relatively few maria on the far side, and this asymmetry is one of the puzzles of lunar geology. Various hypotheses have been proposed, including differences in the thickness of the crust between near and far sides. The near side crust is thinner, making it easier for magma from the interior to reach the surface. Differences in the abundance of heat-producing radioactive elements in the crust and the influence of Earth's gravitational tidal heating on the near side in the early solar system. The precise reason for the Maria asymmetry is still debated. The largest impact feature on the Moon is the South Pole Aitken Basin, located on the far side near the South Pole. It is one of the largest confirmed impact craters in the solar system, measuring about 2,500 kilometers in diameter and about 8 to 9 kilometers deep. It is so large that its formation must have involved a body tens of kilometers across striking the Moon at high velocity, an event catastrophic enough to excavate material from deep within the lunar crust and possibly even from the upper mantle. The South Pole Aitken Basin is of enormous scientific interest precisely because of this depth. Material from depth has been exposed, potentially including samples of the lunar mantle that are otherwise inaccessible. China's Chang'e 4 mission, which landed on the floor of von Karman crater within the South Pole Aitken Basin in January 2019, specifically targeted this region to study the exposed deep crustal and possibly mantle material. Other prominent features include the Oriental Basin on the western limb of the Moon, visible only from orbit or from Earth under favorable libration conditions, a multi-ring impact structure about 900 kilometers across, with concentric rings of mountains surrounding a central dark mare floor, one of the most geographically striking impact features in the solar system. Tycho crater in the Southern Highlands is relatively young in lunar terms, only about 108 million years old, and is the source of a dramatic system of bright rays that extend across thousands of kilometers of the lunar surface, material ejected from the impact and deposited across the surrounding terrain. The brightness of the rays reflects the youth of the material, which has not yet been darkened by the space weathering processes that gradually alter lunar surface materials over time. Mare Tranquillitatis, the Sea of Tranquility, is permanently distinguished as the site of the first human landing on another world. On July 20th, 1969, the Apollo 11 lunar module descended to a smooth, relatively flat region of this ancient lava plain, and Neil Armstrong and Buzz Aldrin became the first human beings to stand on a world other than Earth. The specific landing site, now marked by the descent stage of the lunar module and various discarded equipment, is protected as a heritage site by a NASA recommendation that future missions not land closer than 2 kilometers, preserving the physical record of humanity's first steps beyond Earth. The far side of the Moon is one of the great reminders that closeness does not guarantee understanding. From Earth, the near side dominates our imagination. It is the face we see in the sky, the arrangement of dark Maria and bright highlands that cultures have read as a man, a rabbit, a woman, a tree, a face, or a set of symbolic marks. For thousands of years, that was the Moon. The far side was not merely unseen, it was almost psychologically absent. No one knew whether it looked similar or completely different. In October 1959, the Soviet spacecraft Luna 3 flew around the Moon and returned the first crude photographs of the far side. The images were blurred and low in detail, but they were enough to reveal the shock. The far side did not look like the near side. It had far fewer dark Maria. It was brighter, rougher, more heavily cratered, and dominated by ancient highlands. The Moon was asymmetric in a way no Earth-based observer could have guessed. That asymmetry is now one of the central puzzles of lunar science. Why are the dark volcanic plains concentrated on the near side? Why is the crust thicker on the far side? Why are heat-producing elements, especially potassium, rare earth elements, and phosphorus, the group often abbreviated as KREP, concentrated mostly on the near side? especially around Oceanus Procellarum and the Imbrium region. These are not minor details. They are clues to how the moon cooled, how its crust formed, where radioactive heat accumulated, and why volcanic eruptions were easier in some regions than others. One possibility is that Earth's presence influenced the early moon's cooling. When the moon was newly formed and much closer to Earth, Earth would have appeared enormous in the lunar sky, glowing with heat from its own post-impact molten surface. The near side of the moon, always facing Earth after tidal locking, may have cooled more slowly than the far side because it received thermal radiation from the hot young Earth. Slower cooling could have affected crust formation, leading to thinner crust on the near side and thicker crust on the far side. This idea is still debated, but it shows how intimately connected the moon's geology may be to Earth's early state. Another possibility involves the distribution of the final materials from the lunar magma ocean. As the magma ocean crystallized, incompatible elements that do not easily fit into the crystal structures of the common lunar minerals, would have remained in the last molten residues. These residues were enriched in heat-producing elements. If they became concentrated on the near side, they could have kept that region warmer for longer, making it easier for basaltic magma to erupt and fill impact basins. In that case, the familiar dark near-side maria are not just lava plains. They are the visible expression of an uneven distribution of heat deep in lunar history. The South Pole Aitken Basin on the far side makes the far side even more scientifically valuable. It is not only one of the largest impact basins on the moon. It may have excavated material from deep within the crust or even from the upper mantle. If scientists can analyze samples from this basin, they may be able to study material that normally lies far below the lunar surface. That is why missions to the far side and South Polar region are so important. They are not simply visiting unfamiliar terrain. They are trying to read deeper pages of the moon's interior history. The far side is also one of the best locations in the inner solar system for radio astronomy. Earth is loud. Human civilization fills near-Earth space with radio transmissions, communications, radar, satellites, broadcast leakage, navigation signals. The moon's far side is permanently shielded from direct radio noise from Earth. For low-frequency radio astronomy, especially studies of the early universe before the first stars fully formed, the far side could provide a quiet platform unlike anywhere near Earth. A future radio telescope placed there could listen to wavelengths that Earth's ionosphere blocks and Earth's technology contaminates. So the far side is not just the unseen half. It is a scientific frontier, a record of lunar crust formation, a possible window into the mantle, a preserved archive of ancient impacts, and perhaps one day a quiet listening post for the oldest lightless eras of the universe. The moon's surface is covered by a layer of fragmented material called regolith, a mixture of broken rock fragments, glass beads, and dust produced by billions of years of meteorite impacts. The top layer of regolith, the finest grain material, is sometimes called the lunar soil, though it lacks any of the biological and chemical properties that make terrestrial soil fertile. The regolith layer varies in depth from a few meters in younger mare regions to perhaps 15 meters or more in older highland regions, where billions of years of additional impact processing have produced a thicker, more fragmented layer. It is extraordinarily fine at its surface. The uppermost few centimeters consist of particles typically between 30 and 50 micrometers across, comparable to talcum powder in grain size. This fineness is one of the practical challenges of operating on the lunar surface. The fine regolith is abrasive, clingy due to electrostatic charging in the lunar environment, and penetrates every surface it contacts. Apollo astronauts found it coating their suits, their equipment, and the interior of the lunar module, and reported that it had a distinctive smell, variously described as burnt gunpowder, charcoal, or spent fireworks, an odor probably resulting from the reaction of the highly reactive, unsaturated surface of freshly disturbed regolith particles with the air inside the cabin. Within the regolith are glass beads, tiny spheres of volcanic glass and impact-formed glass produced when rock was melted and then rapidly quenched, either by volcanic eruptions in the lunar past or by the heat of meteorite impacts. These glass beads preserve within them samples of ancient gases and solar wind particles, trapped at the time of formation and surviving in the regolith for billions of years. The study of these glass beads has provided detailed information about the composition of the ancient solar wind, the flux of cosmic rays over geological time, and the volcanic history of the moon. The regolith also contains a record of the sun. Because the moon has no substantial atmosphere and no global magnetic field, its surface is exposed directly to the solar wind, the stream of charged particles flowing outward from the sun. These particles implant themselves into the upper grains of lunar soil. Over millions and billions of years, the regolith accumulates a history of solar activity written in atoms: hydrogen, helium, neon, argon, and other implanted species. A scoop of lunar soil is therefore not only pulverized rock. It is a sample of the sun's long-term behavior. This is one reason the moon is scientifically valuable even when the rocks themselves are not dramatic. A small grain of lunar dust can carry information about impact history, volcanic history, solar wind exposure, cosmic ray bombardment, and the chemical environment of the inner solar system. The surface is constantly stirred by micrometeorite impacts in a process called gardening. Tiny impacts churn the upper layers, burying some grains, exposing others, melting some into glass, and mixing material from nearby and distant impacts into a complex, layered soil. There is no weather in the terrestrial sense, but the moon does have space weather. Solar particles, ultraviolet radiation, temperature cycling, and micrometeorites all alter the surface. Fresh crater rays are bright because newly excavated material has not yet been darkened by space weathering. Over time, the bright rays fade as the surface matures. This is why a crater's brightness can be a clue to its age. The moon is not being eroded by rivers or wind, but it is not chemically frozen. It is slowly processed by space itself. The dust is also one of the largest practical problems for human exploration. Apollo astronauts learned this quickly. Lunar dust stuck to suits, gloves, boots, sample containers, camera equipment, seals, and the inside of the lunar module. It was abrasive because the grains had not been rounded by water or wind. On Earth, sand grains become smoother as they tumble through rivers and beaches. Lunar grains are angular, sharp, broken by impacts, and electrically clingy. They can scratch visors, wear mechanical joints, clog seals, and pose hazards if inhaled inside a habitat. This gives the moon a strangely double character. It is scientifically precious because its surface is so well preserved, but that same preservation creates an environment hostile to machinery and human lungs. The moon's silence is not softness. It is a vacuum full of sharp dust, radiation, temperature extremes, and impact debris. The moon's interior, what lies beneath the surface, has been partially characterized through a combination of Apollo-era measurements and subsequent analysis, but significant uncertainties remain. The Apollo program deployed 4 seismometers on the lunar surface at the Apollo 12, 14, 15, and 16 landing sites, which operated until 1977. Together, they detected thousands of lunar seismic events, meteorite impacts, shallow moonquakes in the upper crust, deep moonquakes occurring at depths of about 700 to 1,200 kilometers, and thermal moonquakes triggered by the dramatic temperature changes at sunrise and sunset as the sun-facing surface expands and contracts. The deep moonquakes are particularly interesting. Unlike shallow earthquakes, which occur because of the movement of tectonic plates, the deep moonquakes occur because of tidal stresses. The same tidal forces from Earth that are slowly moving the moon outward also periodically stress the moon's interior, and these stresses are released as moonquakes. The deep moonquakes occur in regularly repeating clusters associated with specific points in the moon's elliptical orbit, when the moon is at perigee and the tidal forces from Earth are at their strongest. More than 300 distinct deep moonquake source locations have been identified, distributed in a layer at depths of about 700 to 1,200 kilometers. Analysis of the seismic data from Apollo produced the first model of the lunar interior. The crust was found to be on average about 40 to 50 kilometers thick, thicker than Earth's oceanic crust, though thinner than Earth's continental crust. This average conceals a significant asymmetry. The crust on the far side is estimated to be considerably thicker than on the near side, perhaps 80 kilometers thick on the far side compared to perhaps 30 kilometers on the near side. This asymmetry in crustal thickness is thought to be related to the asymmetry in Maria distribution. A thinner near-side crust would have made it easier for magma from the interior to erupt through and flood the impact basins. Below the crust, the mantle extends to the core. The Apollo seismic data suggested that the mantle has two zones, an upper mantle of solid rock and a lower mantle that may be partially molten, still retaining some liquid or very hot plastic rock at depth, even 4 billion years after formation. The persistence of a partially molten lower mantle into the present is evidence that the moon has not fully cooled, and it is consistent with the continuing occurrence of deep moonquakes driven by tidal heating. At the center, the moon has a small iron core, much smaller relative to its total size than Earth's core. The core radius is estimated at about 300 to 400 kilometers, about 20 to 25% of the moon's total radius. Earth's core extends to about 55% of Earth's radius. The moon's small iron core is consistent with the giant impact hypothesis, which predicts that the moon formed predominantly from silicate material with relatively little iron. The Lunar Reconnaissance Orbiter and subsequent gravity mapping missions have refined these interior models by measuring variations in the moon's gravitational field from orbit. A non-uniform interior produces measurable variations in the gravitational pull on an orbiting spacecraft, which can be detected as tiny changes in the spacecraft's orbital velocity. These gravity maps have revealed the positions and sizes of mass concentrations beneath the surface, regions where dense material is concentrated, typically associated with the volcanic intrusions that accompanied mare formation. The Grail mission, which consisted of two small spacecraft orbiting the moon in formation and measuring the distance between them with exquisite precision, produced the highest resolution gravity map of the moon ever made, revealing not just the large-scale structure, but details about the density distribution down to relatively small scales. Moonquakes are particularly important because they show that the moon is not simply inert. The shallow moonquakes detected by Apollo were fewer than deep moonquakes, but some were surprisingly strong and long-lasting. On Earth, seismic waves fade relatively quickly because Earth's interior contains water, fractures, molten regions, and complex structures that absorb and scatter energy. The moon is drier, colder, and more rigid. Seismic waves can ring through it for a long time, like vibrations through a bell. Some moonquakes lasted for many minutes, far longer than comparable earthquakes would last on Earth. That ringing quality tells scientists something about the lunar interior. It suggests a body that is fractured but relatively dry, a world where seismic energy is not damped efficiently. It also creates a practical concern for future bases. A habitat built on the moon would not face plate tectonics, but it would still need to handle shallow moonquakes, thermal stresses, meteorite impacts, and regolith movement. The moon is quiet compared with Earth, but quiet is not the same as motionless. The thermal moonquakes are smaller but elegant. During the lunar night, which lasts about 2 Earth weeks, surface temperatures fall to extreme cold. When the sun rises, the surface heats rapidly. Rocks expand. Cracks shift. The surface makes tiny seismic adjustments to the sudden thermal stress. Apollo instruments detected these events, turning sunrise itself into a measurable geological process. The deep moonquakes are stranger. They occur hundreds of kilometers down, in repeating patterns tied to the moon's orbit around Earth. They are not random. They are synchronized with tidal stress. The moon is being flexed by Earth's gravity, and its interior responds at specific locations, releasing small amounts of energy again and again. These deep events are like the moon's internal tides made audible to instruments. A modern seismic network would transform lunar science. Apollo seismometers were all placed on the near side and mostly in a limited region. They were remarkable for their time, but they could not provide full global coverage. A future network spread across the near side, far side, poles, and perhaps the South Pole Aitken Basin would allow scientists to map the crust, mantle, partially molten layer, and core with far greater precision. It would help answer how large the core really is, how much of the deep mantle remains warm or partially molten, how the far side differs internally from the near side, and whether deep structures left by ancient impacts still shape the moon today. The moon is not speaking loudly, but it is speaking in impacts, quakes, tides, heat, and dust. We simply need better instruments to hear it. Water ice at the moon's poles is one of the most scientifically and practically significant discoveries of the past 3 decades of lunar exploration. The presence of water ice was first suggested by radar data from the Clementine spacecraft in 1994, which detected anomalously strong radar reflections from within permanently shadowed craters near the South Pole, the kind of reflection associated with water ice. The Lunar Prospector mission in 1998 and 1999 detected elevated hydrogen concentrations at both poles using a neutron spectrometer, consistent with the presence of water ice or hydrogen-bearing minerals in the polar regolith. But these were indirect measurements, and debates about whether the signatures were truly indicating water ice or some other hydrogen-bearing compound continued. The decisive confirmation came from the LCROSS mission in October 2009. LCROSS, Lunar Crater Observation and Sensing Satellite, was a deliberately orchestrated impact. The spent upper stage of the Centaur rocket that had launched the mission was aimed at Cabeus crater near the South Pole, where Lunar Prospector had detected the highest hydrogen concentration. The impact excavated material from the crater floor, including from the permanently shadowed region, and threw a plume of debris high above the surface. LCROSS itself flew through this plume immediately after the impact and analyzed the material spectrometrically before also impacting the surface. The results were unambiguous. Water was present in the excavated material at concentrations of about 5.5% by mass, far more than just traces, more than enough to constitute a significant deposit. Subsequent analysis has confirmed and expanded the picture. The lunar poles host water ice in the permanently shadowed regions of craters, regions where the sun has never shone in the entirety of the solar system's history, where temperatures remain permanently below about -170 degrees Celsius, cold enough that water ice delivered by comet and asteroid impacts over billions of years would remain frozen and stable indefinitely. The total quantity of ice at the poles is estimated to be on the order of 600 million tons, a modest quantity by terrestrial standards, but significant for a world without surface water. The origin of this ice is thought to be primarily cometary. Comets are largely composed of water ice, and when they impact the moon, the water released can migrate across the surface toward the poles, In the cold lunar environment, water molecules hop across the surface in a random walk, and those that reach permanently shadowed regions are trapped there. Over billions of years, this gradual accumulation of cometary water at the poles has built up the deposits detected today. Some contribution may also come from the solar wind, which contains hydrogen ions that can combine with oxygen in lunar surface minerals to produce water molecules. And some may come from volcanic outgassing. The ancient volcanic eruptions that flooded the Maria released water vapor along with other gases, some of which may have migrated to the poles. The practical significance of the polar ice extends well beyond pure scientific interest. Water is an extraordinarily valuable resource for any sustained human presence on the moon. It can be used directly for drinking and agriculture. It can be broken down into hydrogen and oxygen by electrolysis, providing both breathing oxygen and rocket propellant. Water is heavy and expensive to launch from Earth. If it can be sourced on the moon from local ice deposits, the economics of sustained lunar operations change dramatically. The polar ice deposits are therefore central to nearly every serious proposal for a permanent human presence on the moon, and their precise distribution, depth, concentration, and physical state are among the highest scientific priorities for near-term lunar exploration. The water ice is not evenly distributed like a frozen lake. It is probably patchy, mixed into regolith, concentrated in some cold traps, absent from others, and protected by layers of dry material. Some deposits may be relatively accessible, while others may be buried, diffuse, or chemically bound in ways that make extraction difficult. This is why the word resource must be used carefully. The presence of water is confirmed. The engineering usefulness of that water depends on concentration, depth, purity, grain size, temperature, and terrain. Permanently shadowed regions are among the coldest places in the solar system. Some crater floors near the lunar poles are colder than Pluto. They have not seen direct sunlight for billions of years. They are dark not only at night, but always. A rover entering such a crater cannot rely on solar panels. It must survive extreme cold, navigate in darkness, communicate with Earth indirectly, and avoid terrain that may be steep, rough, or filled with loose regolith. Studying lunar ice is therefore not just a question of chemistry. It is a challenge of exploration engineering. The ice also has scientific value independent of human use. A cold trap can preserve volatile compounds delivered over billions of years by comets, asteroids, solar wind chemistry, and volcanic outgassing. In principle, layers of polar ice could record changes in the inner solar system's impact environment, the flux of cometary material, and the history of water delivery to Earth and Moon. If those deposits are disturbed carelessly, part of that record could be lost. This creates a tension that will become increasingly important. The same ice that makes lunar bases more practical is also a scientific archive. Future exploration will need to balance resource use with preservation. The moon is not biologically alive, but it is historically delicate. A crater floor that has been cold and dark for billions of years can be changed by the exhaust plume of a lander, the wheels of a rover, or the heat of machinery. The first missions into these regions will not simply explore them. They will alter them. That is why careful mapping comes first. Before large-scale extraction, scientists need to know where the ice is, how it is mixed, how old it is, what other volatiles are present, and how deposits vary from crater to crater. The moon's south pole is not one simple target. It is a landscape of illuminated ridges, shadowed pits, ancient impact structures, steep slopes, temperature traps, communication challenges, and scientific promise. The human history of observing the moon stretches back to the earliest evidence of human cognition. Markings on bones and cave walls that appear to track the lunar cycle have been found at archaeological sites dating back tens of thousands of years, suggesting that tracking the moon's phases was among the earliest systematic intellectual activities of our species. The moon's 29.5-day synodic cycle, the time from one new moon to the next, is a natural unit of time, visible and predictable, that served as the basis for calendars in virtually every ancient civilization. The word month is derived directly from moon in numerous languages. The moon was a constant presence in ancient religion and mythology across cultures. Lunar deities, the Mesopotamian moon god Nana, the Egyptian Khonsu, the Greek Selene and Artemis, the Roman Diana, the Hindu Chandra, the Aztec Tecusistecatl, were central figures in religious traditions on every continent. The moon's apparent influence on tides, on menstrual cycles, on the behavior of nocturnal animals, and on plant growth were recognized long before science had the tools to properly characterize any of them. The word lunatic preserves the ancient belief that the moon could influence human mental states, a belief that modern science has found no mechanism to support, though the persistence of higher rates of certain emergencies in emergency rooms on full moon nights remains a subject of occasional study, with inconclusive results. The telescope transformed humanity's relationship with the moon as it did with all astronomical objects. Galileo turned an improved telescope on the moon in 1609 and 1610 and produced detailed sketches showing mountains, craters, and what he recognized as a complex, three-dimensional terrain. He was the first to see the moon not as a perfect sphere, as classical philosophy had insisted all celestial bodies must be, but as a world with topography, with shadows that revealed elevations and depressions, with a character that was geological rather than otherworldly. His sketches, published in Sidereus Nuncius in 1610, were a revelation. The moon was not smooth, not uniform, not fundamentally different in kind from the terrestrial landscape. It was rough and varied and, in some sense, real in a way that abstract celestial spheres had never seemed. Over the following centuries, telescopic mapping of the moon became increasingly detailed and systematic. Giovanni Riccioli and Francesco Maria Grimaldi produced in 1651 the first comprehensive map of the moon using the nomenclature system still in use today, naming the dark regions Maria, naming features after scientists and philosophers, and establishing the systematic approach to lunar nomenclature that has been maintained and extended through to the present. Virtually every major astronomer of the 17th, 18th, and 19th centuries spent time mapping and studying the moon, and the detail of lunar maps improved steadily as telescope technology improved. The question of how the craters formed was debated for centuries. Volcanic origin was long favored. The Earth's surface shows volcanic calderas, and volcanic eruptions seemed a natural explanation for the circular depressions observed on the moon. The impact hypothesis, that the craters were formed by the impact of meteorites and asteroids, gained ground slowly through the late 19th and early 20th centuries, supported by increasingly compelling arguments about the geometry, distribution, and physical characteristics of the craters. The definitive demonstration came from laboratory experiments, computer simulations, and ultimately from direct examination of impact structures on Earth, and the impact origin of lunar craters is now established beyond any scientific doubt. The Apollo program was the most ambitious scientific and engineering enterprise in human history, and its scientific legacy, often overshadowed by the political and cultural dimensions of the program, remains substantial more than 50 years later. Between 1969 and 1972, 6 Apollo missions successfully landed on the moon and returned with samples, while one mission, Apollo 13, was aborted after an oxygen tank explosion and its crew returned safely to Earth. 12 human beings walked on the lunar surface during this period. They set up scientific instruments, collected geological samples, drove a lunar rover, photographed and described the terrain in person, and planted the foundation of modern lunar science. The Apollo program began in earnest in May 1961, when President John F. Kennedy addressed Congress and announced the goal of landing a man on the moon and returning him safely to Earth before the end of the decade. The announcement was political in origin, a response to the Soviet Union's early successes in space, particularly Yuri Gagarin's orbital flight just weeks earlier. But the scientific justification was real and was articulated clearly by the scientists and engineers who shaped the program. A decade of intense engineering development, the Saturn V rocket, the command module, the lunar module, the spacesuits, the navigation systems, the life support, the communications, culminated in Apollo 11's successful landing on July 20, 1969. Neil Armstrong's descent from the lunar module and first steps on the lunar surface were watched on live television by an estimated 600 million people, about a fifth of the world's population at the time, one of the largest shared experiences in human history. His words upon stepping from the ladder onto the surface, "That's one small step for man, one giant leap for mankind," were reportedly intended to include a man, a small grammatical distinction that was lost in transmission and has been debated ever since. Armstrong and Aldrin spent about 2.5 hours outside the module, collecting samples and deploying instruments, before returning to the module and preparing for the journey home. The scientific harvest of the Apollo program was immense. The missions returned approximately 382 kilograms of lunar material, rock cores, surface samples, and regolith from 6 geographically distinct locations across the near side. These samples have been studied by scientists for more than 50 years and continue to yield new insights as analytical techniques improve. The oldest Apollo samples date to more than 4 billion years ago, among the oldest solid material of any kind that can be directly examined in a laboratory. The study of these samples has been fundamental to developing our current understanding of the moon's formation, the history of the solar system's bombardment, the composition of the lunar interior, and the processes that shape planetary surfaces. The Apollo samples are especially powerful because they allow scientists to connect orbital maps to laboratory reality. A spacecraft can measure color, brightness, topography, gravity, neutron flux, gamma rays, and infrared spectra from orbit. These measurements can suggest composition and age, but a rock in a laboratory is different. A sample can be cut, polished, dated, heated, dissolved, scanned, and measured atom by atom. Minerals can be identified with precision. Isotopes can be compared. Tiny inclusions trapped inside crystals can preserve chemical environments that no camera could ever see. This is why the Apollo collection continues to matter. The samples were not used up in the 1970s. Many were sealed, stored, and preserved for future techniques that did not exist when they were collected. Decades later, scientists can analyze them with instruments far more sensitive than anything available during Apollo. A grain that once seemed ordinary can become valuable when a new method can measure isotopes at parts per million precision. The moon keeps giving new results because the samples are real pieces of another world. One example is zircon. Zircon crystals are tiny but extraordinarily useful because they can survive geological processing and incorporate uranium while excluding lead when they form. Over time, uranium decays into lead at known rates. By measuring uranium-lead ratios, scientists can determine when the zircon crystallized. Lunar zircons help constrain the age of the lunar crust and, indirectly, the timing of the moon's formation and magma ocean crystallization. A small crystal can carry a date from the first solid crust of another world. The samples also revealed that the moon was not as dry as once believed. For decades, the moon was described as bone dry, and early sample analyses seemed to support that idea. But later studies of volcanic glass beads and mineral inclusions found hydrogen and water-related signatures inside lunar materials. This changed the story. The moon's interior may contain more water than early Apollo-era interpretations suggested, though still far less than Earth. That water has implications for the giant impact, for lunar volcanic eruptions, and for how volatile materials survived or were lost during the moon's formation. Lunar samples also anchor the crater counting method used across the solar system. On worlds where we cannot return samples, scientists often estimate surface ages by counting craters. Older surfaces have more craters because they have been exposed longer to impacts. But crater counts need calibration. The moon provides that calibration because we have both cratered surfaces and radiometrically dated samples. When scientists estimate ages on Mars, Mercury, or icy moons using crater density, lunar samples are part of the foundation beneath those estimates. This means the moon is not only a subject of study, it is a measuring tool for planetary science. It helps date other worlds. It helps interpret impact histories. It provides ground truth for remote sensing. It is the reference body for much of our understanding of rocky surfaces across the solar system. Beyond the sample return, the Apollo missions deployed several science packages on the lunar surface. The Apollo Lunar Surface Experiments packages, or ALSEPs, included seismometers, magnetometers, heat flow probes, and laser-ranging retroreflectors at each landing site. The retroreflectors are still in use today. The ongoing Lunar Laser Ranging Experiment, which bounces laser pulses off the retroreflectors and measures the round-trip travel time with extraordinary precision, has provided some of the most precise measurements ever made of the moon's distance, motion, and rotation. It is through this experiment that the 3.8 centimeter per year recession of the moon has been measured, and through which constraints on general relativity and on the moon's interior have been derived. The Apollo 15, 16, and 17 missions, the J missions, equipped with the lunar rover and more extensive scientific objectives, produced particularly rich scientific results. Apollo 15 landed near Hadley Rill, a sinuous channel carved by ancient lava flows, and collected samples from the highlands adjacent to the mare. Apollo 16 landed in the Descartes Highlands, the first mission to land in the lunar highlands specifically, and its samples showed that the highlands are dominated by anorthosite, as the magma ocean hypothesis predicted. Apollo 17 landed in the Taurus Littrow Valley and included Harrison Schmitt, a professional geologist, the only trained geologist ever to walk on the moon, who conducted detailed field geology during the mission. The Apollo program ended with Apollo 17 in December 1972, the last humans to leave Earth orbit until future missions returned to the moon. The end of the program was driven by budget cuts, political shifts, and the waning of Cold War urgency after the United States had clearly won the race to the moon. The scientific community at the time argued for continuing Apollo. There was more science to do, more geological diversity to sample, more of the moon to explore, and was overruled by political and budgetary considerations. The remaining Saturn V rockets and Apollo hardware were placed in museums. The 50-plus years since Apollo have not been scientifically quiet, however. Robotic missions from the United States, the Soviet Union, Europe, Japan, India, China, and Israel have explored the moon from orbit and, in several cases, from the surface. The Soviet Luna program, running parallel to Apollo, deployed rovers and conducted sample return missions robotically, returning small quantities of lunar soil to Earth. The Clementine mission in 1994 produced the first global maps of the lunar surface in multiple wavelengths. Lunar Prospector in 1998 to 1999 discovered the polar hydrogen deposits. The Lunar Reconnaissance Orbiter, operating since 2009, has produced the most detailed maps of the lunar surface ever made. with resolution sufficient to image the Apollo landing sites and the equipment left behind. India's Chandrayaan-1 confirmed water ice at the poles. China's Chang'e program has landed rovers on both the near and far sides, and in 2020 returned the first fresh lunar samples since the Apollo era, about 1.7 kilograms from a mare region called Oceanus Procellarum, providing the first sample from this geologically significant region. The return of humans to the moon has moved from distant aspiration back into active spaceflight. The Apollo era ended in December 1972. For more than half a century afterward, no human being left low Earth orbit. The moon remained close in astronomical terms, but distant in human practice, visited by robots, mapped in exquisite detail, sampled indirectly through meteorites and older Apollo material, but not crossed again by astronauts. That gap is one of the stranger facts of modern space history. The first generation reached the moon with 1960s technology, and then the species stepped back for decades. The new lunar era is different from Apollo in almost every way. Apollo was a Cold War race, compressed into a single political decade, aimed at proving that a landing was possible and that one nation could do it first. The current era is slower, more international, more commercial, and more focused on sustainability, science, resource assessment, and infrastructure. It is less cinematic in the old heroic sense, but potentially more consequential if it leads to repeated missions rather than a brief series of flags and footprints. NASA's Artemis program began with Artemis 1, an uncrewed test flight of the Space Launch System rocket and Orion spacecraft around the moon in 2022. Artemis 2 then returned astronauts to lunar space with a crewed flyby, testing deep space life support, navigation, communications, and spacecraft operations before any attempt to land. The harder step is the surface return, landing astronauts near the lunar South Pole, operating in difficult lighting and terrain, and connecting the mission to longer-term exploration systems rather than a single short visit. The South Pole remains the center of attention because it combines scientific and practical value. Permanently shadowed regions may contain water ice. Nearby high ridges and crater rims can receive long periods of sunlight, making solar power more practical than in many other lunar locations. A base or repeated landing zone near the South Pole would allow astronauts and robots to study polar volatiles, test resource extraction, deploy seismometers, drill into cold trap deposits, and learn how to operate in one of the most extreme environments accessible to humans. But the South Pole is not easy. The sun stays low on the horizon, producing long shadows that make navigation difficult. Temperatures can change sharply over small distances. Communication with Earth may require relay satellites, depending on the terrain. Landing safely in a region of steep slopes, crater rims, boulders, and shadow requires navigation far more precise than Apollo needed in the broad Mare Plains. The very features that make the region valuable also make it difficult. Commercial lunar missions have become part of this new phase. NASA's Commercial Lunar Payload Services program uses private landers to deliver science instruments and technology demonstrations to the surface. The first successful American commercial lunar landing, Intuitive Machines IM-1 in February 2024, was imperfect but historically important, returning the United States to the lunar surface for the first time since Apollo and showing both the promise and difficulty of commercial landers. These missions are not replacements for government exploration. They are part of a broader ecosystem in which science payloads, navigation experiments, communication systems, and resource prospecting can be tested more frequently. Other nations have changed the lunar landscape as well. India's Chandrayaan-3 successfully landed near the South Polar region in August 2023, making India the fourth country to soft land on the moon. Japan's SLIM mission demonstrated precision landing technology in 2024. China's Chang'e program has become one of the most scientifically productive lunar programs of the modern era, including Chang'e 4, the first successful landing on the lunar far side, and Chang'e 6, which returned the first samples from the far side of the moon in 2024 from the South Pole Aitken Basin region. Those samples are especially important because they come from a region that may expose deeper lunar materials than the near-side Apollo and Luna sample sites. The moon is therefore no longer only an American historical object or an Apollo memory. It is a global scientific frontier again. Different nations and companies are approaching it with different goals: geology, resource mapping, technological demonstration, prestige, long-duration infrastructure, radio astronomy, and preparation for Mars. Some of those motives are scientific. Some are political. Some are commercial. Most are mixed. That is how major frontiers usually work. The scientific opportunity is enormous. New samples from regions never visited by Apollo can test models of lunar volcanism, far-side crust formation, impact basin history, and the timing of the late bombardment. New seismometers can finally produce a global picture of the moon's interior. Polar missions can determine whether water ice is accessible or merely present. Far-side radio instruments can use the moon as a shield against Earth's radio noise. Human field geology can return, this time with better instruments, better training, and landing sites chosen not only for safety, but for scientific power. The risk is that the moon becomes busy before it is fully understood. Every landing disturbs the surface. Every engine plume moves dust. Every rover track becomes part of the geological record. The moon preserves footprints for millions of years because it has no wind or rain. But that same preservation means exploration itself becomes permanent. The next era of lunar exploration will need rules, restraint, and scientific planning if it is to study the moon without needlessly damaging the records it contains. This is what makes the present moment so important. The moon is close enough for repeated missions, old enough to preserve the early solar system, useful enough to matter for future exploration, and fragile enough that the first decisions of this new era may shape how future generations inherit it. There is another future role for the moon that receives less public attention than bases and ice mining: the moon as an observatory. The lunar far side is shielded from Earth's radio noise. That alone makes it one of the most valuable places in the inner solar system for certain kinds of astronomy. Low-frequency radio waves from the early universe cannot be studied easily from Earth's surface because Earth's ionosphere blocks or distorts them, and because human radio transmissions create interference. A radio array on the far side could listen in a quiet environment, using the moon itself as a natural barrier. One of the most ambitious goals would be to study the cosmic dark ages, the period after the cosmic microwave background was released, but before the first stars and galaxies fully illuminated the universe. During that era, neutral hydrogen filled space. Its faint radio signal, stretched by cosmic expansion, could carry information about the universe before starlight. Detecting that signal is extremely difficult, but the far side of the moon may be one of the few places near Earth where such observations could be attempted with enough radio quiet. The moon is also valuable for optical and infrared astronomy in certain ways, though it presents challenges. It has no atmosphere, which means no atmospheric blurring, no weather, no clouds, and no airglow. A telescope on the lunar surface could have stable observing conditions, but lunar dust, temperature swings, micrometeorites, and the long day-night cycle complicate operations. The moon is not automatically better than free space for every telescope. It is better for some specific purposes, especially where the surface can provide stability, shielding, or infrastructure. The polar regions could also host instruments designed to monitor the Earth-Moon system itself. Laser ranging arrays, seismometers, heat flow probes, volatile detectors, and radiation monitors. A long-lived scientific network on the moon would not only study the moon. It would study space weather, meteoroid flux, solar activity, cosmic rays, and the interaction between Earth and its natural satellite over decades. This is the deeper meaning of returning to the moon. It is not only about going back to where Apollo went. It is about turning the nearest world into a scientific platform, a place to study planetary formation, Earth's history, the early solar system, volatile delivery, deep cosmic radio signals, and the practical limits of living beyond Earth. The moon is close enough to teach us repeatedly and far enough to be another world. That combination is rare. The moon still holds questions that decades of observation and analysis have not fully answered. The precise details of the giant impact remain uncertain. Different models make different predictions about the size of Theia, the angle of impact, the proportion of material from Theia versus proto-Earth that ended up in the moon, and the timing relative to the moon's formation. The oxygen isotope similarity between Earth and Moon is particularly challenging. If the moon formed from a mixture of proto-Earth and Theia material, and if Theia had a different oxygen isotope composition from proto-Earth, as would be expected if Theia formed at a different distance from the Sun, the mixed material that formed the moon should have a different oxygen isotope ratio from either parent body. The fact that Earth and Moon have nearly identical oxygen isotope ratios requires either that Theia had the same ratio as proto-Earth, a coincidence that requires explanation, or that the material was thoroughly homogenized during the impact, which requires specific impact conditions, or that subsequent geological processes redistributed isotopes in ways that created the similarity. Each of these explanations has been explored, and none has been definitively established. The origin of the far side-near-side asymmetry, why the crust is thicker on the far side, and why the Maria are concentrated on the near side, is not fully explained by any current model. Several mechanisms have been proposed, but constraining them requires data about the far side that is still limited despite Chang'e 4's successful far side landing. Future missions targeting the far side, particularly to the South Pole Aitken Basin where deep crustal and possible mantle material is exposed, would provide critical information. The distribution and total quantity of polar water ice is still being characterized. While the presence of ice is established, the depth of the ice deposits, their physical state, ice mixed through the regolith versus solid ice lenses buried beneath regolith, their precise concentration at various locations, and whether they are accessible to practical extraction are all still being determined. Future missions, including lunar rover missions specifically designed to explore permanently shadowed regions, are needed to fully map these resources. The detailed seismic structure of the moon's interior remains poorly constrained. The Apollo seismometers were limited in number, in location, all on the near side, and in sensitivity. The InSight mission's experience on Mars, using a single, highly sensitive seismometer to characterize Mars's interior, has demonstrated what a single, modern seismometer can accomplish. A seismometer network deployed across the lunar surface, including on the far side, would characterize the moon's interior with a precision that the Apollo measurements could not achieve, potentially resolving debates about the extent of the lower partially molten zone, the size of the core, and the nature of the deep moonquake source regions. The moon also matters because it helps us think about planets beyond the solar system. Astronomers have found thousands of exoplanets, but exomoons remain extremely difficult to detect. A moon is much smaller and fainter than its planet, and its signals are subtle. Tiny changes in transit timing, transit duration, or light curves. Several candidates have been discussed, but confirmed exomoons remain beyond our current observational reach in most cases. Yet the Earth-Moon system tells us that moons can matter enormously for planetary environments. A large moon can affect tides, rotation, axial stability, climate rhythms, and perhaps even the long-term habitability of a planet. If a rocky exoplanet orbits in its star's habitable zone, the presence or absence of a large moon may change how stable that planet's climate is over long timescales. It may change tidal environments, day-length evolution, and the planet's response to perturbations from other planets in the system. This does not mean every habitable world needs a moon like ours, but it does mean that habitability may be harder to understand if we ignore moons. The moon is unusual because it is large relative to Earth. Most moons are tiny compared with their planets. Jupiter's Galilean moons are large in absolute size, but Jupiter is enormous. Earth's moon is different because it forms almost a double planet-like system in terms of relative scale. The barycenter, the common center of mass around which Earth and Moon orbit, lies inside Earth, but not at Earth's center. The moon is not a small pebble captured by a planet. It is a major companion. This has implications for planetary formation. Giant impacts may be common in young planetary systems. If such impacts can create large moons, then Earth-like moons may exist elsewhere. But if the conditions required are narrow, the right impactor size, angle, velocity, timing, and material composition, then moons like ours may be relatively rare. We do not yet know. The moon may represent a common outcome of rocky planet formation, or it may represent a fortunate accident. That uncertainty matters. When we ask how common Earth-like worlds are, we often focus on planet size, orbital distance, atmosphere, and water. But Earth's history is entangled with the moon. A true Earth analog might not be simply a rocky planet in the habitable zone. It might be a rocky planet with a large stabilizing moon, a history of impacts that delivered the right materials, a carbon cycle, oceans, a magnetic field, and a long period of climate stability. The moon reminds us that a planet is not only a sphere orbiting a star, it is part of a system. And there remains the deeper question of what the moon's origin tells us about Earth's history and about planetary formation more broadly. The giant impact that formed the moon was not just a geological event for the moon. It was one of the most transformative events in Earth's history. It determined the angular momentum of the Earth-Moon system, which in turn determined the length of Earth's day and the rate of tidal evolution. It set the composition of Earth's mantle by removing iron into the moon's orbit and then removing much of it further into space. The late addition of a veneer of meteoritic material after the giant impact may be responsible for Earth's current abundance of siderophile elements, iron-loving elements like gold, platinum, and iridium that would otherwise have been sequestered in the core. The moon's formation is, in a profound sense, part of the story of what Earth is and why it has the properties it does. There is also a more uncomfortable question beneath the practical plans. What kind of place will the moon become if human activity expands there? For most of history, the moon was untouched by human hands. Then Apollo left landing stages, flags, footprints, scientific instruments, discarded equipment, and tracks from lunar rovers. Later robotic missions added new impact sites, landers, and debris. In the coming decades, there may be many more. Communications relays, power systems, landing pads, resource prospecting sites, rovers, habitats, science stations, and perhaps eventually industrial equipment may appear on a surface that has preserved almost every disturbance for geological timescales. This does not mean the moon should remain untouched forever. Exploration changes places. Science requires contact. Human presence beyond Earth will not happen without physical infrastructure. But the moon's preservation makes responsibility unavoidable. A footprint is not washed away. A landing plume does not disappear into weather. A historic site does not heal. The moon remembers everything placed on it. The Apollo sites are not only national monuments. They are archaeological sites for the entire species. They preserve the first physical evidence of humans operating on another world: boot prints, tools, descent stages, experiments, rover tracks, and the patterns of movement made by astronauts learning how to work in 1/6 gravity. Future missions will need to avoid damaging them, not because the past should stop the future, but because a species that reaches other worlds should be capable of remembering how it first did so. The same is true of scientifically sensitive regions. Permanently shadowed craters, volatile rich deposits, unusual magnetic anomalies, fresh impact sites, and far-side radio quiet zones may all need protection from careless interference. The Moon is large, but the most valuable regions are not evenly distributed. Many missions will be drawn to the same polar zones because the ice, lighting, and terrain make them attractive. Coordination will matter. This gives the Moon a new kind of significance. It is no longer only a subject of astronomy or geology. It is becoming a test of how humanity behaves when it has access to another world. Do we treat it only as a resource? Only as a monument? Only as a laboratory? The answer will probably be all three, and the challenge will be balancing them intelligently. Let's take a moment to consider the Moon in deep time, not the 4.5 billion years of the solar system's past, but the far future. The Moon is currently moving away from Earth at 3.8 centimeters per year. In 500 million years, the Moon will be about 20,000 kilometers farther away, a change of about 5% in the Earth-Moon distance. This would slightly reduce the Moon's apparent size in Earth's sky and slightly weaken its gravitational influence on Earth. In a billion years, the distance increases by about 40,000 kilometers. These changes are modest on cosmological timescales, but over the 5 billion years before the Sun enters its red giant phase, the total recession would be about 200,000 kilometers, adding roughly 50% to the current Earth-Moon distance. By the time the Sun begins to expand as a red giant, in about 5 billion years, the Moon will be considerably farther from Earth and Earth's rotation will be considerably slower. The Moon itself will probably survive the Sun's red giant expansion, unlike the inner planets Mercury and Venus, which are likely to be engulfed, and Earth itself, whose fate is uncertain. The Moon's larger orbital distance from the Sun may allow it to escape direct incorporation. But the changing luminosity of the red giant Sun will have dramatic effects on the surfaces of both Earth and Moon. And whatever the Moon looks like at that distant time, it will be a very different place from the world that reflected the light of our familiar yellow star back to a blue world below. In the near future, in human historical terms, the Moon is unchanging in any meaningful sense. Its orbit will shift by a meter or two in a century. Its surface will accumulate a few new impact craters, invisible to the naked eye. The polar ice will continue to slowly accumulate. The deep moonquakes will continue their tidal rhythm. And in the human future, decades rather than billions of years, the Moon will be visited again. Boot prints will join the Apollo footprints in the South Polar regolith. Drills will sample the permanently shadowed ice for the first time in situ. Seismometers will map the interior with unprecedented detail. The first buildings constructed on another world will perhaps take shape near the peaks that receive near-continuous sunlight. And scientists will study the lunar samples returned by Artemis missions with the same careful attention that researchers have given to Apollo samples for more than 50 years, finding in them, as researchers keep finding in the Apollo collection, new information about the solar system's earliest history. Even the simple act of looking at the Moon from Earth is more complicated than it appears. The Moon seems bright, but its surface is actually dark. Lunar soil reflects only a small fraction of the sunlight that falls on it, roughly similar to worn asphalt. It looks bright in our sky because it is close and because it is set against the darkness of night. The full moon can illuminate landscapes, cast shadows, and change the behavior of animals, but the surface itself is not white. It is gray, dusty, and darkened by billions of years of space weathering. Its brightness also changes with angle. Around full moon, the surface appears especially bright because shadows vanish when the sun is almost directly behind the observer. Rough surfaces, tiny grains, and the way light scatters through regolith produce what is called the opposition effect, a sudden increase in brightness when the phase angle is very small. The full moon is not just a half-lit ball seen face-on. It is a complex optical surface, reflecting light through a powdery layer shaped by impacts and vacuum. This matters because the moon teaches a recurring lesson in astronomy. Appearance is not reality. The bright highlands are older than the dark Maria. The smooth plains are volcanic, not seas. The quiet face is impact-battered. The familiar near side is only part of the story. The dark side is not always dark. The moon looks close and simple, but almost every simple impression dissolves under careful study. That is exactly why it remains interesting. The moon is the object humanity knows best beyond Earth, and yet it still contains unanswered questions about origin, water, interior structure, polar volatiles, far-side geology, and future exploration. The better we know it, the less it becomes a symbol and the more it becomes a world. And perhaps that is the strongest reason to keep returning to it. The moon is close enough for engineering, old enough for geology, stable enough for long-term instruments, and familiar enough that every new discovery feels personal. It is not a distant abstraction. It is the nearest piece of cosmic history we can still reach. The moon is not a dead rock. It is a world that has been shaped by 4.5 billion years of remarkable history, that continues to actively interact with Earth through tides and gravitational torques, that holds within its rocks and its polar ice chemical records of the solar system's past and resources for humanity's future. It is the most accessible astronomical body beyond Earth, close enough to reach in 3 days with current technology, familiar enough in its appearance to feel almost domestic, and yet scientifically rich enough that dedicated researchers have spent entire careers studying lunar geology, lunar chemistry, and lunar history without exhausting what the moon has to offer. The quiet companion. Always there, always circling, always changing too slowly for unaided human perception. Moving almost imperceptibly away, a few centimeters each year, reflecting the light of the sun from a surface that has preserved 4.5 billion years of violent history. It has been present for everything that has happened on Earth. Every ocean that formed and retreated, every mountain range that rose and eroded, every mass extinction, every bloom of new life, every human culture that looked up and gave it a name. The moon has been here for all of it, pulling the tides, slowing the day, steadying the axis, marking time in the sky. And now it is becoming something else as well. Not only an ancient companion, but a destination again. A place where science, history, technology, and human ambition are beginning to meet on real ground. The moon is close, but it is not simple. It is quiet, but it is not empty. It is familiar, but it is still not fully understood. For now, it continues its slow orbit around Earth, bright on some nights, hidden on others, carrying impact scars, polar ice, ancient lava plains, Apollo footprints, far-side mysteries, and the memory of Earth's own beginning. And we leave it there, the nearest world, the oldest witness, and the first step beyond Earth. Good night.